So this is the last portion of chapter 3E, combining first law and second law. I even named this, it's not in the textbook chapter, but I'm just saying that it's all about G, okay? It's all about G. So if I do the G, based on the Born cycle and so on, you will see that VDP minus SDP. And this one has a lot of meanings according to this kind of law. So, so this chapter is not really needed, but I guess it's kind of pave a way to think about this one. And this equation will be used in chapter 4, chapter 5, and so on. It's going to be used in forever. So they just want to give a little prelude on this. So once again, this is a... okay. So what is all about this is I want to know, let's say, pressure dependence of G. Right? So this is a probably natural question. And second one is temperature. So temperature dependence of the G. Okay? So these are the two things that can be taken from this simple equation. It's already saying something to me, right? Change in the Gibbs free energy change in response to changing the pressure. Changing the pressure, keeping the other term constant, which is a temperature constant. And what do you call what this one corresponding to? Volume, right? So I can see that. And what about temperature dependence? That must be an entropy. So changing the G, changing the temperature, so I'm changing this, and keeping the pressure constant is a minus S. And then one thing that now we need to bring our physical insight. What is the sign of this? Is it positive always, or it can be negative?
Positive.
Volume is always
Positive.
positive, right? So this is always positive. What about what? Entropy. Entropy is always bigger than 0, right? Entropy is always positive. Right? The 0 entropy is defined by second law thermodynamics, perfect crystalline solid at 0 Kelvin, which is not attainable. Other than that, everything is just a positive. So this is a opposite sign, so it's a negative. Right? So this one is a starting point, and this equation is going to be very, very useful for us to begin with. But let's say I want to start with the first one, okay, first one, and bring the concept about this. So I want to know pressure dependence. And so once again, the volume is an indicator for changing the Gibbs free energy, change of pressure, keeping the isothermal pressure change, G. And there are two categories. One is called incompressible fluid. Something that can be deformed is an incompressible fluid. Second one is compressible fluid. Okay, so those are the two different, I guess, a term that I can use. What is an example of compressible fluid? You guys know? Compressible means what? You apply the pressure, volume is changing. What kind of example of compressible fluid is, you know? Anyone? And you apply the pressure, you see quite a nice volume change. You call it what? You call that is? What? I mean, you just know liquid, gas, solid, right? So what are you going to call that? This is?
Gas.
This is a gas, right?
Compressive.
And not only that, the volume, when you apply the pressure, is going to be P over nRT. I know exact relationship on this, right? So that can be an example, and I can poke that in and then see how the G is depending on the pressure, on the constant temperature. So I'm in business. What about the incompressible fluid? What are the examples? That's right. So, I mean, think about it. You have a liquid here, you apply the pressure. Do you see the volume change? I mean, yes, you can make it with an enormous one, right? So with your normal physical forces, you only see small change in the volume. So what I can say, volume is constant. It makes a very big difference in the equation above. So, and then they also want to know, okay, so I'm going to modify this equation because I want to deal with the per mole changes. So molar gives free energy. Later, I think that in the chapter 4, the molar gives free energy is going to be a chemical potential. Now you start to hear something that is getting something useful. Chemical potential for single component system, not mixture. Okay? Single component system, and that I'm going to deal with it. So this is actually going to kind of have it will be very useful. So I'm going to just use a molar gives free energy. So I guess I can still say molar volume is constant. So therefore, changing the molar Gibbs free energy is nothing but molar volume times delta P at P is constant. Very boring equation, but it works. Okay, so you can say the liquid, like water, what's the molar volume, and you apply the pressure. So make sure you use a liter, you use an ATM or something, and then this unit is a liter ATM, or if you want to use this one, make sure you use a Pascal. That's a joule. I mean, that's the details about how to get the answers done, but this is the way that when things are incompressible. When things are compressible, so I'm going to change this to molar. Okay? So this is a 1. And then let's put that in. So changing the G is Vm times dP. So Vm is nR over P and the dP on the constant temperature, right? So in the temperature constant. So this is an isothermal. So we are changing only one variable. So now this partial differential becomes the normal differential. And then what do? I'm changing the initial pressure, final pressure. Okay. So can you guys get the final answer? Delta, I guess this is delta Gm, right? Delta Gm, nR. So that's the equation. We are getting something very actually. This is the one that is going to be important when we're dealing with vapors, right? Vapor has a gas, and the gas has a chemical potential. This is an equation that we are using. So we'll get back to you on that. So that was the pressure difference. And this equation will show up again, but let's say Sm, so it's a molar, round T, round Gm, under ambient pressure condition. So this is a conceptual part, the entropy negative, right? So what I mean is, when I draw this, let's say this is your Gm, and this is a temperature under constant pressure. Which is correct? Number 1, number 2? Is it going to go up or go down? For any gases, any liquid, it all goes down, right? That's what it means, because this was a negative slope, right? Negative slope. When you use a x as a t, y as a gm, you should get this slope negative. Okay, here. So now I'm going to draw two. 1, 2. These are the two. And one is, let's say, solid. Solid has the entropy, right? The other one is, let's say, gas, which is molar entropy. Which one is bigger in magnitude? This one, right? And so if I put a negative sign to the one, which is the slope is much more steeper decrease. So which one is a gas? Here, right? Which one is a liquid? Or solid. So this is solid, and this is a gas. I got that, right? And if you compare these two, and then what about the liquid? Liquid should have entropy in between in terms of magnitude, right? Solid is much more ordered, so they have a smallest entropy, losing the lattice, more disordered, flying around, it's even more disordered, right? So this is something in between. So I'm going to draw slope of, let's say, -1, -10. This is like a -6 or -5. So this is my liquid. Okay. And then for this is actually, I actually cover the entry portion of the next chapter. This is same as chemical potential for single component, okay? So you look at that, chemical potential means, the electrical engineer has the electric potential, right? Chemist has a chemical potential, which is a kind of energy state, and they want to minimize their potential as much as I can. So if I go there, I have at this temperature, I have a choice being solid, liquid. I guess the gas is way up there. Right? Which one that, as a matter, I'm going to choose? I want to choose to be this one. This is my state that has the lowest chemical potential among choices of solid, liquid, and the gas. Okay? And what about here? Gas is the lowest, right? And what about in the between? That is your liquid, right? So therefore, when they are meeting each other, this is a case where their potential of solid and the liquid is the same. And this is what we call fusion temperature, somebody call melting temperature, you can call it that way. And this is the one temperature where you have a liquid and the gas or vapor is have the same chemical potential. So we call boiling temperature. That's it, right? So this is something that we start to get to know and get to use this. So that's a one use for getting us to use. And there's another one that I'm going to use, and then that's going to be a little ugly here. It's going to be very important. So here, okay. So it's all about now the G, and okay, this portion, fine. I think that I can do it. This portion, okay, this is more like a philosophical statement which is going to draw, but it's not so useful as far as I'm concerned that what else can I use this? And there's another equation that people come out. So those are the two, my starting point, but second one going to be a different form. Okay? So now the temperature dependence, so that's a temperature dependence. The temperature dependence in the form of a 2-second one. And this is actually has a so important, it has a name. It's called the Gibbs. Helmholtz equation. So whenever you guys see this name, they put a lot of thought onto it. Or in a way, this one is actually not so intuitive in the beginning, so that's why they actually put an emphasis on this. Okay, so my starting point is Gibbs free energy change. Putting the pressure constant is minus S. Okay. But now so that's a temperature dependence on the Gibbs free energy, right? So now I'm asking you, instead of for you to looking at the G, I'm asking you to see, well, if they thought about it, right? And instead of the G, I want to do G over T. That's another Gibbs free energy, just Gibbs free energy transformed into some other form. So the G divided by T is another Gibbs free energy analog, right? Kind of form, and I want to do this differential on this. So that's also sort of the temperature dependence. Right? I would say sort of, right? But this is the one going to be very useful. Right? Why? Because of you will see me what's the consequence of this. So if I do that, so I'm going to go back to my drawing board. So this must be a G over T is nothing but Gibbs free energy, which is a temperature function, multiply temperature, right? So it's like these two products, F times G, right? You guys doesn't need to do that. You will see the final form that is useful, but I need to drive this one. So as far as I'm concerned, I'm going to take F and an F prime, which is 1 over T derivative, that's a minus on this. And then what else can I do? Plus, I'm going to do, I will take the derivative